Lab 6 is about mapping and path planning. The mapping half of the lab will use sensor readings to detect nearby walls and use Monte Carlo particle filter localization to help calculate which grid cell the robot is in. Once it finds its location, it'll map out the walls around it and fill in the internal wall configuration of the maze. Once it gets through the whole maze, all the walls should show and be printed. The path planning portion of the lab will use a wavefront planner algorithm to first plot out which shortest path the robot should take from a starting cell to a goal cell, and then sending that path instruction to the robot so that it can run them. The initial grid layout will be known for the path planning, but not for the mapping sections. For task 1, it's the mapping section, the wall mapping, so I use a combination of algorithms to find where the robot is and then mark that cell as visited, as well as all the walls that I detected at the time. In the end, the robot should have all the cells marked as visited, and the entire internal wall configuration should be stored for printing. Here's task 1, where we'll map the internal wall configuration using the sensor readings, localization algorithms, and wall detection. Before we run the whole maze, I'll explain the grid print and wall layout so you can understand what's happening as the robot moves. So step 1. Alright, so each one of these groups represents a grid cell on the maze. The question marks in the middle are the unvisited cells, and the 1s and 0s around them represent walls. A 1 means there's a wall detected, and 0 means there wasn't. At first, only these outer walls around the perimeter are set, and it's my job to map out what the internal walls look like. Once a grid cell is traveled to, the question mark is replaced by a V for visited, and the 0s are changed to 1s if a wall is detected by the distance sensors in any of the 3 directions where we have them. Since we started at the bottom right at cell 16, you can see that its question mark is updated to a V on that first step, and the 0-1 representation shows walls to the southeast and no walls to the northwest. All free space that the robot can travel to is 0s, so that looks accurate. Now I'm going to play the next. Alright, so once we got to that next cell, it's cell 12, you can see that the question mark is now a V, but more importantly, the left sensor detected a western wall, so that west value for the cell was changed from a 0 to a 1. That's how this robot tracks the internal wall configuration. So by the time every cell is marked visited, the robot will stop and all the internal walls will be mapped to 1s by the robot. Under each grid print, the robot pose is also going to be there. And the pose shows the XY value of the grid cell number, and the IMU readings in degrees. So it's gone from 16 to 1 so far, and these 2 walls were mapped in with the left distance sensor, and so were these 2 walls with the left distance sensor. Now it's on its way this way. It's going to be mapping these walls. Alright, all cells were visited, and the robot stopped. Looks like the internal walls were mapped correctly. Moving on. For task 2, we start with a known grid, so for the map, we already know where all of the free space and walls are ahead of time. And instead of traveling every cell in the grid, we're just gonna go from a start cell to a goal cell. The objective is to use the wavefront planning algorithm to develop a path for the robot to travel before sending it off to follow that path you generated. The point of the wavefront planner is to find the shortest path through the maze from the given start cell to the given goal cell. So I'll be running mine with a mix of cases where some of them have 2 possible shortest paths, so they're the same distance from start to goal, and some cases where there's only one obvious shorter path. But of course, a little bit on the wavefront algorithm first. So there's two types of wavefront algorithms that I learned about: 8-point connectivity on the left and 4-point connectivity on the right. You can see here that the 8-point connectivity has 8 yellow neighbors, one at every single square that's touching the blue cell, whereas 4-point only has the neighbors at its north, south, east, and west. These adjacent neighbor cells are where the robot can travel to on its next step, so if you plan on driving your robot diagonally through the maze, you'd use 8-point connectivity in your algorithm. Here's how that works. To start the wavefront planner, you set all free space cells on the known map to a value of 0, all obstacles and walls to 1, and the goal cell alone gets the value of 2. They happen to be color-coded as well on these examples, with the free space being white, the obstacles red, and both goal and start cells set to blue. From there, it's a matter of starting at the goal cell and setting all the free space or 0 value neighbors to that cell to the cell's value plus 1. So another way of putting that is any white square next to the current cell gets a value increase of the current cell plus 1. So here you see the blue goal cell on the bottom right, and every neighbor next to that goal that's used to say 0 is now set to 3, taken from the goal's value of 2 plus the 1. You repeat this process over and over so that the cells next to the 3s become 4s, and their neighbors become 5s, and then 6 and 7, etc., until all the 0s that are on the map are gone from the reachable grid space. Once you've eliminated all the 0s, it's going to look something like this, and it's time to plan your path. So beginning from the start cell on the top left, the shortest path can be found by locating whichever neighbor has the lowest value and then moving to that one, and rinse and repeat. So since our start point has a value of 18, we're looking for an adjacent cell that gets us closer to 2, so we move to a 17, and then we look for a 16 and a 15 all the way down until we get to 2. You wouldn't go from a 17 to another 17 when you have the option of a lower 16. And there are many paths through here from 18 to 2, but the shortest ones will avoid that type of repeating numbers. My Task 2 algorithm uses the same concept with 2 key differences. One, since my robot isn't going diagonally through any cells, it uses the 4-point connectivity rather than 8. So the neighbors are only the cells that are up, down, left, and right of it. And 2, I'm using a 9x9 grid to represent the maze that we have. So for this example, the grid has 2 shortest paths, and with some of the test cases I run with my robot, my algorithm just picks whichever one of the paths randomly and sends the robot to go through the motions. So let me show you that now. Before we begin, I wanted to show you this funky image here because this is how the known 4x4 maze is going to be represented in my 9x9 wavefront planner. So the 1s are the wall obstacles, and the 0s are the free space that the robot can travel over. In this first test, our starting cell is going to be here at 16, and the goal cell is going to be 10. But rather than run the whole full path just yet, I will show you the very first steps the robot takes, because that's where the wavefront planner does all its calculations for the shortest path that it thinks we should take. So if we scroll up to the top here, at the top you'll see the initial grid with the only value of 2 being the goal cell here, which is 10 on this map. In the first step, we take all the neighbors of the goal and set them to 2 plus 1, so you see the 3s here next to that. Step 2, those cells' neighbors get set to 4, then 5, then 6, and so on, until there's no more 0s. This specific path, given the specific goal and start points that we have here, takes 14 steps to weed out all the 0s, and you still got the 2 at your starting point. Then it starts finding the shortest path by starting at the goal and seeing which neighbor has the lowest value and moving there all the way up until it gets back down to 2. This here is the path that printed out the steps that I mean. The actual robot steps take every other instruction there as a motion, because it's only a 4x4 grid that we're actually running through, where my matrix is 9x9. So where the plan says to go up 6 times in a row here, we're really only moving the robot up 3 squares from where I'm at, so 1, 2, 3. And here is that plan that's printed out in steps, cut down for the robot to understand. So this path print here that's highlighted is the actual path that the robot gets sent to execute. I'll run the whole deal now so you can see how it all plays out. Okay, so the path that was given from the wavefront planner is printed out here along with the direction that the robot's facing at the time. And when it reached the goal, it stopped and printed goal. Next test that we do, I'm going to start at cell 16 again, but we'll switch to a different goal cell. Alright, here we are. Our start point is set to cell 16, but our goal is now set to cell 6, which is up here. I talked enough, so I'll just let it rip. Alright, so it went from 16 to 6, and we have all the prints there. I'll go to the top real quick. Initial was changed. Should take a different amount of steps now. No, it took 14 steps again. Our path that was printed is a bunch of lefts, an up and a right, which fits. That's what was printed, and it was followed, it reached goal. I'll try one last one, and let's try to cover this top column since we haven't traveled there yet. For the last one, I thought it'd be fun to cover the top row, so we're going to start at cell 13 on the bottom left here and drive all the way up to goal cell number 1. And this is one of those cases where there is 2 shortest paths. It could either take 9 steps to go north from 13 and zigzag its way up to 1, or it can go east immediately all the way around the grid. Either way will take 9 steps, so I'm sure it's going to choose whatever's clever. I haven't run this one yet, so we'll see what it decides to, which path it decides to take. Looks like it shows up instead of right. Okay, we successfully reached the goal again and went from 13 to 1. This one looks a little bit longer, so let's see how many steps it took. Alright, so this one took 18 steps to weed out the zeros. This is our long path planned from the wavefront planner. Here is the edit so that the robot knows which squares to take, and these were printed along the way, and it reached the goal. So the wavefront planner gave us another good path, and the robot delivered on it. That's the final lab wrapped. Thanks for watching.